So if for whatever reason you need to see my video as well as hear me, find my video among the participants and pin my video. Okay. So this is the fourth and final talk in this series, and I'm going to talk about the how to actually prove a Birch type theorem using a repulsion strategy, and I'm also going to say a few words about what the advantage is of that repulsion strategy are supposed to be. So I can see some difficulty pasting the correct links into the chat, so I hope people will be able to figure that out. But in theory, I have put the links in the chat to view either with a browser or with an app. Okay. So the starting point for all of this was this theorem of Birch, and the desire to reduce the number of variables needed to get this nice asymptotic formula for the number of integral solutions to some homogeneous equations. And the idea is that repulsion enables you to do this, and in particular for degrees 4 or higher, Piatic repulsion turns out to be the right way to go about this, and it has some other advantages that I'll talk about at the end of today's talk. And this, so I'm up to slide 3 now, for those on the online version. So this is this was the core of Birch's strategy, to go from an exponential sum being large to the number of solutions to a certain system of Diophantine inequalities being large, and from there to getting a rational approximation to this parameter alpha that goes into the exponential sum. And I asserted that sort of the reason that I think there's room for improvement here in this part of Birch's argument is that when one goes and shows this, one has this system of linear inequalities, which so that alpha, your vector that you're trying to approximate, times a matrix of integers is close to an integer vector. And my claim was that one ought to be able to interpret this as a condition not just on alpha, which is what Birch does, but also on V. And in some sense, this should give more room as capital R grows larger. And that last part I wasn't really successful in justifying, but that's the claim I'm making. And repulsion from this point of view is finding a special case, that is when alpha is in a region of 0, when you can really do this and actually do it in a kind of trivial way, when you can force V to be 0. Or in the case of Piatic repulsion, when you can force V to be congruent to 0 mod P. Okay, so it's realizing that room for improvement by imposing some conditions on alpha, which make it much easier to interpret this as a condition on the vector V. And And so on slide 4, then, we have the whole strategy laid out for using repulsion to prove a result in the style of Birch. So we see now the definition of this exponential sum, and this counting function that we want can be expressed as the integral of this exponential sum over the unit hypercube. And we have this formulation of the sort of circle method part of Birch's argument in a way, which says that we only need to understand the measure of the sets where this exponential sum is large. And here we have a Piatic repulsion lemma, which says that if our vector alpha lies in a Piatic neighborhood of the origin, which means a union of small boxes like this, where the boxes have size about capital P to the minus d, capital P being the size of our integer variables in our original problem. So these two conditions mean really that these boxes are of size capital P to the minus d, and the distance between these boxes is little p to the minus e, where little p is a prime and a parameter, and e is a natural number and a parameter. Okay. And what the lemma says is that if you're on a neighborhood of the origin like this, and the exponential sum is large, then you actually have to be in the little box next to the origin. So I'm thinking here of only taking boxes which are contained inside the unit hypercube. In the lemma, what it actually says is that the box has to be centered at an integer point. And what I'm thinking here is that we're taking, so here's 1, and we're sort of only looking at these boxes which are sort of not touching the boundary up here. So we're looking for boxes which are really contained inside the unit hypercube, and then the only box that the exponential sum is allowed to be large on is the box next to the origin. And I mentioned last time that this encapsulates a kind of typical intuition in the circle method, that the exponential sum should only be large when alpha is close to a rational number of small denominator, and if instead alpha is close to a rational number of reasonably large denominator, so if the smallest common denominator that you can have here when this thing's in lowest terms is divisible by a large prime p, for example, then this exponential sum actually ought to be small. Okay, and that in a way is what this is saying. And so I mentioned that the strategy to actually go out and show that the part of the unit hypercube on which this exponential sum is large, the method to show that that is not so large is to tile the unit hypercube with translates of this Piatic neighborhood of the origin, and by using a modified Weil differencing step, one can show that for each of these translates, there can be only one of the little boxes on which the exponential sum is large. if one sets up all the parameters correctly. Okay, so we're going to see how to do that rigorously today. So let me have one last go at pasting this. Okay. No, I think my copy paste is cursed, so I can't get the correct links into the chat. Okay. So one thing that I wanted to say about this is that one can also get a perspective just from this information alone on why repulsion should be superior to the original argument when the number of forms is large. So this is that in this Piatic repulsion argument, we only ever use properties of linear combinations of the forms. We never really treat this form with this system of forms as a vector. We only use properties of we only really use properties of sort of one particular linear combination of the forms. So in the assumptions in the lemma, we have that our parameter beta has to be close to a rational vector b on p to the e, and then the only linear combination of the forms that we really use any properties of here is is this one here. So we divide the vector b by the GCD of its elements to get by the largest power of p that divides all its elements, to get something which is a vector of coprime integers, integers at least one of which is coprime to p, integers which aren't all divisible by p, and then this linear combination of the forms is the only thing that we actually used any properties of in the proof. And somehow this means that the proof operates exactly the same for one form as it would for a system of several, because we only actually care about this particular form with integer coefficients. Okay, so let's take a slightly more detailed look at how to apply this. So here we're going to, so this is slide 5 now, we're going to try to make rigorous what I said before about covering the unit hypercube with translates of a Piatic neighborhood of the origin. So the translates are going to be called B subscript L. So let me draw this as a picture here. So our basic neighborhood of the origin is going to be B subscript naught. So that's this gray neighborhood here, and its translates are going to look like this, where so this displacement from the center of one of the gray cubes to the center of one of the blue cubes, this displacement is L on p to the e plus d minus 1. So this is a slightly funny looking normalization, and one should think of this as essentially being capital P to the D. So this is essentially L divided by capital P to the D. Which is, so the reason that it's this funny thing is that in the proof of this Piatic repulsion lemma, it's natural to take the size of these little boxes to be something like 1 on a power of the prime little p, and then you want the displacement to be the smallest displacement to be about the same as the size, so that you're covering the whole unit hypercube without too much overlap. So one should think of B subscript L as being your basic neighborhood displaced by something like L on capital P to the D, where L here is an integer vector. So we have so in this definition of B subscript L, it's a union over something called A. So A here is the displacement from the box that's nearest to the origin to the box that we're actually in. So L is the displacement from from the origin, or from a box in our basic neighborhood of the origin that's nearest the origin to this one, and A is then the displacement to some other box in our blue translate. So that's also normalized. It's normalized by P to the E. Because the displacement between different boxes in the basic neighborhood has to be 1 on P to the E. Okay. And then we have some ranges for these things. So the range for A is chosen so that we basically get all the boxes we can that fit inside the unit hypercube. And the range for L is chosen so that we cover the whole unit hypercube without the boxes overlapping each other too much. So we can get boxes sort of out to here, and there might be a little bit of overlap at the end, but not too much. Okay. And then what we do is we have this set capital A subscript L, and that's the points in one particular colorful neighborhood. So I'll fill in some more. So A subscript L is the points in one particular colorful neighborhood such that the exponential sum is large. And large just means the usual thing, which comes from the definition of the set whose measure we need to be small. Okay. And what we want to do is we want to show that for each L, this measure is small. And like I advertised, what this is going to mean is showing that each of these translates, each of these sets BL only one of these little boxes can actually meet AL. So the exponential sum can only actually be large on one box in each colorful neighborhood. Okay. So what we do is we take two different points in the same colorful neighborhood on which the exponential sum is large. So maybe one of them is here and one of them is here. And so these are alpha and alpha plus beta. So I have put, so this is a comma, not a primed, slightly unfortunate typesetting. So this box is B subscript LA, and this box is B subscript LA plus B. So we have a displacement between these two boxes in the same colorful neighborhood. And what we want to do is show that this integer vector b is 0, so that these two yellow boxes containing a point where the exponential sum is large are actually the same point. And the way that we do this, so we're going to now start making assumptions on the size of the prime little p. So it's at this point the prime is still a parameter, but we're going to choose it sufficiently large but not too large. The reason for this is on slide 6. Okay. So what we want is we want to be able to apply our Piatic repulsion to show that because the exponential sum is large at both of these 2 points, and because these 2 points are close together in Piatic sense, they differ by more or less a rational vector with denominator dividing p to the e. So they recall like this, where the gaps between these yellow boxes are of size 1 on p to the e, and the boxes are of size p to the minus d. So what we need to do is we need to satisfy this first hypothesis up here. So we need to make this number of solutions to this
Simon, I think you're muted.
My internet failed, perhaps at the same time. Maybe we should send him a text. Can anyone else see his screen? Because I cannot.
I see the screen and I see him. He seems to be talking and it says that he's muted.
Well, I think one of his devices dropped out. I mean, he said he had 2 different devices, one for audio and one for video.
I can't see his screen on the Zoom, but I can see it on the Google Jamboard thing.
Does anybody have the ability to unmute him? He's still
Because
showing.
that device is not connected, I can't either mute or unmute him, but I can request him to mute, and I think he's aware of this.
Okay, it looks like my Zoom app crashed, which is new. I'm unable to share my screen because my Zoom app crashed and I'm already sharing my screen. Seems like a very circular problem. Can somebody who's host or something forcibly unshare my screen? Ah, okay, it seems to have gone. Okay. Okay. So I assume that I am back now. So where were we? Right. So I was saying that the reason for this constraint on the size of the prime is that we want to be able to put this bound on the size of the bad set and this bound on the size of as it were, the good set, the solutions to our Fountain inequalities. We want to put them together to show that the one set is larger than the other. And we'll be able to do that using because we know that the exponential sum is large at both of these 2 points. We'll be able to do that if the prime is sufficiently large. So somehow when the prime is large, we're saving less because we have to use more copies of the, I think this is sort of a reasonable thing, because when the prime is large, we're going to have to use more copies of our neighborhood of the origin to cover the unit hypercube. And I think that's sort of what's going on here. There's a loss there. And that's why we have to have the prime sufficiently large. Okay. So, right, so under this condition on the size of the prime, we can put all the various yellow underlined things together to show that the number of solutions to these Diophantine inequalities is bigger than the bad set. And also, if we've chosen our parameters, so our A's and our L's and the denominators here, in such a way that the other hypotheses of Lemma D are also satisfied. So this gives us the conclusion of Lemma D, that this rational approximation to the displacement has to be basically an integer, and then our range for A, that is our a collection of boxes contained in one of the colorful neighborhoods, ensures that the displacement has to be 0, and so our 2 points are in the same little box. And that's what's written down here. And when we put this together, what we find is that because the ALs together cover all of the points where the exponential sum is large, we get a bound for the measure of the set where the exponential sum is large, which looks like this. So the green part is to do with the measure of one of these boxes. So for each colorful set, we can have one box on which the exponential sum is large, and the blue part is to do with the number of colorful sets. And this yes, again, R, because there are boxes in the R-dimensional unit hypercube. So looking at slide 7, we have the same argument repeated, but brought to a conclusion. So what goes on here is that we have, so here I've just worked out what that measure turns out to be. So the numerator and denominator cancel, and we find that the measure of this super level set, the measure of the subset of the unit hypercube on which the exponential sum is large, is at most is big O of little p to the minus ER. And E is a parameter that we haven't chosen yet. The size of E comes from this condition here. So what's going on here is that these two pink conditions are the same as these two pink conditions. We need the second two pink conditions so that the first two pink conditions hold. And in order for these two to hold, so this is the one which I said was essentially saying that the little boxes are of size capital P to the minus D. So in order for them to hold, we need E to be not too large, which makes sense because that restricts the size of a saving we can get. And it turns out that this choice will work. So we choose, it's not I think completely clear that this is the right thing. It's not immediately obvious that this is the right thing to do, but there's nothing really going on here. If one writes down these two conditions and thinks about it for a while, this pops out as a fairly sensible size for E and for P. And then if we plug that into our bound for the measure, we find that what we've proved is that the measure is of this size here. And that's what I've written in the statement of this corollary. Okay. and there's a condition on K here. So that comes from the requirement that E is at least 0. So I said that this size for E pops out naturally, and E is supposed to be a natural number since everything is modulo P to the E, and that turns into this condition on K that appears in the corollary. Okay, and this, in fact, this looks very much like the kind of bound that we required in our sort of super level set measure approach to Birch's method earlier, which, as I sort of gestured towards before, isn't surprising because this interpolates between two bounds which are both fairly natural. Okay. So in particular, on the 8th slide, we can put this corollary together with the lemma on the measure of super level sets that we saw before, to get this asymptotic that we want whenever this fraction here is less than 1. So to be precise, what we need, so this thing is d times 2 to the d times capital R divided by n minus capital R plus 1, all multiplied by k. And it's this part here that multiplies k. We need this to be less than 1 in order to apply our super level set lemma A that we had before. And this turns out to be exactly this condition that we saw in the theorem before. Okay. So that's how to use Piatic repulsion to improve on Birch's theorem. And something that I wanted to say in the last part of the talk is some other reasons why this approach via super level sets and Piatic repulsion might be interesting. Okay. So one has to do with systems of forms with differing degrees. So there are, I mentioned before, I think that there's work of Browning and Heath Brown extending the result of Birch to systems of forms with potentially different degrees. And this has also been extended by Frey and Madrisch to forms of differing degrees with coefficients in number fields. In fact, this Piatic repulsion approach not only gives an improvement on those results, but actually, I think, simplifies the proof of those results a lot. So I haven't focused on this so much because there's a bit more setup, and I haven't written down all the details yet. But the idea is like this. So we're looking still at a system of equations f of x equal to 0, where for simplicity we'll take the f's to be homogeneous forms. And now we'll take these homogeneous forms to have various different degrees. So write f2 for the part of f consisting of forms with degree 2, and so on up to f capital D for forms with degree capital D, which is supposed to be the largest degree that we see. And for each little d, for each degree, we'll say that there's r subscript little d forms with that degree. And so I continue to use dot product notation, which now works like this. So the vector alpha is broken up into a bunch of subvectors depending on the degree. and each one gets a dot product taken with the forms of degree d, so that this is a general linear combination with real coefficients of all of the forms. And in fact, this super level sets approach, it still works in much the same way. So the analog of the major arc bound that one needs is this that's written here. And other than that, everything sort of works in a very similar way. So the difference, really the main difference notationally is that one needs to be have major arcs which are different sizes in different degrees. So the different parts of the vector alpha have to lie within different distances of rational vectors with the same denominator. Okay. And as I say, sort of making the appropriate changes, the level set approach from before will go through. And so what one needs is a version of this modified repulsion that works in different degrees. So this is very much the proof of this is very much inspired by the work of Browning and Heath Brown, who so this is from I seem to have placed the date. Sorry about this. What is the date of this? I apologize. Well, I apologize for this. I've mislaid the date of this paper. It's somewhere in the vicinity of 2016, I believe. And the idea is that if you have provided this this counting function, which is associated to the degree capital D part, is sufficiently large, and provided the sort of the high degree parts of beta are sufficiently small. So sorry, this is a conclusion, not an assumption. I said that wrong. So the idea is that we have always that the top degree part, we have the usual kind of thing. So in the top degree part, the top degree part, the system of Diophantine inequalities associated to the top degree part of F is always large in the way that we had before. And moreover, if the top several betas, if the betas associated to the high degree parts of F are small, then we can say the same for the low degree parts as well. Okay. And this turns out to be enough. The idea is to do a kind of induction where you first show that the displacement in the top degree part is small, and then go down and by induction show that the lower degree parts are small as well. So the final condition that one has in order to get an asymptotic in this setting is this thing here. So this is the analog of little c being less than 1. BD here is the dimension of the variety. So this is the maximal dimension as let's say beta, or maybe I should call it gamma, excuse me, as let's say gamma runs over c to the r without 0 of the dimension of the singular locus grad so this should be c to the r d and then I want to take a linear combination with complex coefficients of the degree little d part. Okay, there we go. So this is the maximal dimension of a singular locus associated to the degree little d part. So one can think so this thing is typically going to be fairly small if the underlying system of forms is nice. And in fact, using the work of Browning and Brown, we get that we can bound these b to the d's in such a way that the condition becomes this thing that's written here. Okay. And in particular, this is a slightly neater statement than the number of variables that was previously required, as well as being smaller when say one of the little RDs is large. It actually seems to be smaller in many cases just when the total number of forms is large as well, even if the number of forms in a fixed degree is not so big. Okay. So another interesting aspect, and this is the final slide, of Piatic repulsion is that unlike real repulsion, it has a natural generalization to number fields. So here again, I've sort of glossed over this because there's a lot of notational setup. But the underlying idea is really the same as for forms with coefficients in the rational numbers. So what one wants to do is take a system of forms with coefficients in a number field K, or perhaps I should have said the ring of integers of a number field K. Our analog of the unit hypercube is it's a kind of hypercube over this set here. So we want to take the I want to tensor the number field with real numbers to get some vector space, and then our analog of the unit hypercube is going to be a set in V to the R. So I'm back with, for simplicity, I'm back with a single degree now. And then we have, so Piatic repulsion is now going to work with a prime ideal. And a lot of the, so the key governing quantity is the size of the finite field associated to that prime ideal. Okay, And so our exponential sum, I've written what it looks like here. To sum over vectors with k integral entries, and with size going up to capital P. And size now means, so one way to think of this is that if you write x as a sum of, you take an integral basis of the number field omega I, and you write x as a sum like this with respect to the integral basis, then you think this condition here, one way to think of it is that it just means that all of these integer vectors go up to capital P. And essentially the same thing. The norms are equivalent, and with a smooth weight, you can just move between them. Essentially the same thing would be this, where you take the size of an algebraic number in K to be the maximal size of any of its embeddings into C. Okay. So in this setup, you have this exponential sum where we have to take the trace before putting anything into our complex exponential. And in the same way as before, we can write our counting function as something like an integral. Well, write it as an integral like this over a suitable set. I suppose for consistency, I'll call this alpha. Like this over a suitable set and with respect to a suitable measure. And our Piatic repulsion then is almost just a translation of what we had before. The main difference is that so this should be p to the minus e, I think. Right, yes, that's right. Yes, so that should have been a p to the minus e. Right, so the main difference is that instead of taking a rational with denominator dividing p to the e, you take a number. You take a number in k, which is in p to the minus e for the prime ideal p, so in this setup, you get essentially the same conclusion, with everything being denominated in terms of the size of the finite field instead of the size of the prime. Okay. And this gives, in the end, the same number of variables. In terms of, for a non-singular system of forms with coefficients in a number field, the number of variables will be as it was in Birch's result. So the analog analog of Birch's result over number fields was developed by Skinner. Okay, so that's all I have to say. So thank you very much for the invitation and the opportunity to speak here. And I look forward to answering any questions after the talk.
Thank you, Simon. So, are there any questions for Simon?
Okay, so we have a question about this S alpha plus beta. So let's see if I can find a slide on which this is displayed reasonably nicely. Okay, I think probably this is the best bet. So the question is, as I understand it, whether this step here involves the homogeneity of the forms. And the answer is sort of yes and no. So it is tempting to see this as going from S of alpha plus beta. So I'm just being a little lazy and using inconsistent notation, S of alpha instead of S of alpha dot F. It is tempting to see this as going from S of alpha dot beta to S of beta. And in a sort of moral sense, perhaps this is what's going on. But this very much isn't what one actually sees at in the proof of this. So what one gets is by a Weyl differencing process, one rewrites this product of exponential sums as an exponential sum like this, where the leading term, so the term of highest degree, is beta dot F. So really what one does is one writes it, what one really does is one goes from this to a sum of exponential sums that look like this. That's sort of what one does. And this doesn't really use the homogeneity. But as I say, there are a bunch of lower order terms in here. So you will certainly lose any information that you had about lower order terms in F, because they'll be completely obscured by these lower order terms that appear here. So I hope that makes some sense. And this argument, as I say, is in so this is in my Inventiones paper somewhere. If one wants to look at how exactly it operates.
Okay, good. So there are so few of us that I don't think a breakout room will be necessary, but maybe some people want to ask more questions after the recording has been stopped.